Okay, hi, this is another video where I'm going to take you through the 2011 math questions, question 2 and question 3 specifically. Now, I hope my explanations are nice and clear. I always find that I'm really stretching myself trying to explain my reasoning on math and step because let's face it, they're hard papers, they really are. But yeah, this one actually starts off quite gentle, I think, this question in a way, but it escalates and it gets weird and it's abstract. Anyway, let's have a look at question 2. So we're told x satisfies this equation, so it's a root for that equation. Now, we're going to use this fact throughout this whole question, a bit like on the next question, where it's easy to think that some things don't apply for the whole question. But no, generally speaking, in the math, if they give you a fact and they don't mention that explicitly doesn't apply in parts, then it still applies. You know, the x satisfies this equation for the whole question. And then what they've done is they've said show that x to the 4 equals x plus 2x squared. Well, you know, I'm sure you can see going from straight from there to there. I mean, like, you know, it's such a silly question. You kind of think, well, it's almost too obvious. Of course it does. I just need to multiply the equation by x. So, you know, obviously you're going to multiply the equation by x there. Let me write my answers here. So I'm going to start with star x cubed equals 2x plus 1. And I'm just going to multiply by x. I'm even going to tell the examiner I'm doing that just because I want to make it real obvious that I understand why that's the case as required. It's a bit harder to get their next statement, which is x to the 5 equals 2 plus 4x plus x squared. But, you know, immediately I'm thinking, well, I've got an x to the 5 and you know, I guess I'll try timesing by x again. I get x to the 5 equals 2x cubed plus x squared. And I think, well, I've got an x squared in the answer, but I need to replace my x cubed with 2x plus 1. So that's why they're getting a slightly different answer there. That's how we get rid of the cubic term. So x cubed times 2x plus 1 plus x squared. And so we end up with their answer now. X to the 5 is going to be, now they're writing it from the lowest term up to the highest power of x, 2 plus 4x plus x squared. Good, job done. So first part should be easy, but it's about, there's always going to be a part of a math or step question where suddenly it gets difficult. And that's the next bit really. Now they're saying here, for any k greater than or equal to 0, so for any power in x, you can uniquely write it as a quadratic. That's interesting. Notice we just did that here and here. We wrote x to the power 4 as a quadratic. We wrote x to the power 5 as a quadratic. And there's only one way of doing that. Now, initially, our x to the power 5 was cubic, but then we used this previous answer to turn it into a quadratic. Well, we're going to do a similar kind of approach here. You know, in part A, it's shown that these were the unique values. In part B, you know, and also those were the unique values for x to the power 5. Now, we're going to show that a to the k plus 1 equals ck, b to the, you know, I keep saying 2 there, sorry. A subscript k plus 1 equals c subscript k, b subscript k plus 1 equals, and so on and so forth. We've got to prove these results. Yeah. Okay, well, initial thoughts. I'm going to write down x to the k equals ak plus bkx plus ckx squared. And I suppose I can times it by x once again to get an x to the k plus 1. So that's going to equal akx plus bkx squared plus ckx cubed. Now, our problem is we're not ending up with a quadratic, which is what we really want, because every value for k is greater than or equal to 0 can be expressed as a quadratic. That's really saying. We've got a cubic here. Well, that's slightly disappointing. But did we not show that x cubed was 2x plus 1? That's clearly the secret to this question. That they're trying to give you a big hint as well. They do give hints in these questions, like with the style of the question, the way it's asked. They're giving you a hint about how to sort this out. So I'm just going to replace now my x cubed with the 2x plus 1. And then I'm going to collect like terms and, well, you know, and collect it so it's all in that nice neat format. So we've got, you know, term independent of x, x and x squared. Now the term independent of x here is going to be the ck. So I'm going to write at the start, just so it's kind of clear. The x terms are ak and 2ck, because we've got x times by ak plus 2ck. And then our x squared term is just bk. And I've written it out in that nice format. Now what I can do is I can use essentially a method of equating coefficients, because remember, when they tell you that this is true, it helps actually to kind of like label some of your equations with like labeling, so that you can see what's going on. I mean, like sometimes I do things like I call an equation star, or I call it smiley face or something like that, because I'm communicating with the examiner. But if I call this one, oh, they've already used star, haven't they? That's why star. Let's call it diamond. Yeah. I can say from diamond, what I can also do is just replace all k plus 1s for k's. So xk plus 1 also equals ak plus 1 plus bk plus 1 x plus ck plus 1 x squared. Because then I can start equating coefficients. So I'm going to tell the examiner that's what I'm doing, equating coefficients. Now, what do we have here? We've got ak plus 1 equals ck, because those are the coefficients on the term independent of x. And then you've got ak plus 2ck equals bk plus 1. So bk plus 1 equals ak plus 2ck, and that's exactly their answer, which is reassuring. And finally, ck plus 1 equals bk. Happy days. Now, if you make it through that part of the question, you're probably going to do quite well on this question, I think, because I don't think the rest of it is too tricky. Okay, 3. Let dk equal ak plus ck minus bk. Okay, very well. dk equals ak plus ck minus bk. And we're letting that be the case. Okay, now I'm going to show that dk plus 1 is the negative of dk, and hence that this result is true. So that's what I'm going to try and do. Okay, I'm just going to immediately launch into some kind of a connection, because if I've got to show dk plus 1, then I really need to think about how this works for dk plus 1. So I'm just going to replace all k's for k plus 1s. Good, good, good. And now I can actually plug in the values which I've already shown are true, the ones which are underlined above, because that looks like a nice, a nice thing to do next. So I'm going to get ck, because then I can hopefully turn it into the negative of dk. Here, ck plus 1, well, that's bk. bk plus 1 is the only awkward one, that's ak plus 2ck. Lo and behold, 2ck minus 2ck is minus ck. We've got a plus a bk and then a minus an ak. And notice that that is the negative of dk, because it's the negative of all that. It's all that with the signs changed as required. So I'm just using, part 2 here. Maybe we should tell the examiner that's what we're doing, using the result in part 2. Okay, and hence that this is true. Okay, right, let's do that next. Now, there's probably various ways you could do this, but the way I've decided to go about it is to look at the following. By inspection, and this is back from the previous result, x to the power of 1 is going to be 0 plus 1 times x plus 0 times x squared, because they said for any k greater than or equal to 0, this is true, yeah? And so I'm finding what x to the power of 1 equals. Now, this may not be the best way of doing it, but this is an approach I ended up taking. And it just seemed like a natural approach to me because I wanted to see why this sign was alternating. Okay, cool. So we can then say, so thus D1, because we've got A1 is 0 here, B1 is 1, and C1 is 0. What we can then do is say, okay, so, oh, I put the 1 in the wrong place there, I need down as a subscript. That's D1 equals minus 1, because it's A1 plus C1 minus B1, yeah? Okay, we can now see, so D2 must be positive 1. D3 must be negative 1. D4 must be positive 1. And so on and so forth, etc. Yeah? And what am I using there? I'm using the result I've just proved, yeah? By previous result. Oh, that's nice. And hence, AK plus CK minus DK, well, sorry, minus BK. Remember, that is DK, is just alternating its sign, yeah? And it's starting off with a minus 1 to the power of 1, yeah? When k is 1. So that's, we're in the right point, if you see what I mean. When k is 1, that's going to give us a minus 1. When k is 2, it's going to give us a positive 1. When k is 3, it's going to give us a negative 1 again, and so on and so forth. That's the way we generate the sequence minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. So, it stands to reason now, and hence I can just derive the result now by adding the bk to the other side. And that looks nice and straightforward. I think when I checked my answers, it looks slightly different to the way they were doing it in the mark scheme, but there we go. It seemed, logical to me to do it like that. Okay, part 4. What have we got here? Fk is AK plus 1 plus CK plus 1. Now, I was surprised how nice this part of the question was, because my approach was to sort of say, okay, well, if that's true, then f of k plus 1 equals AK plus 2 plus CK plus 2. Yeah, that stands to reason. Now we need to show that, I'll write down the f of k plus 2 formula. That would be AK plus 3 plus CK plus 3. Yeah. And I kind of figured, well, if I can now just get rid of my AK plus 3s and CK plus 3s, writing them in terms of like Ks and K plus 1s, then I should be, in a strong position kind of thing. So let's just use this. Now, remember, we can use any of these results up here. I'm trying to keep these red ones underlined just in the screen. I have trouble keeping them in the screen. I might even write them down again, because they're useful to use in this part of the question, because obviously they're how you go from the next term to the last term. So AK plus 3 is the same as CK plus 2. And CK plus 3 is the same as BK plus 2. Okay, so I've done that. I've got that kind of boiled down. Now, if you look, I'm trying to make it the same as, what I had before. So I probably want to go all the way down to k plus 1. So I'm going to go CK plus 2. Well, that's the same as BK plus 1. And BK plus 2, that's the same as AK plus 1 plus 2CK plus 1. And so we have this expression here, yeah? Now, we've got f of k plus 2 here, we've got f of k plus 1 here, and we've got f of k here. So now let's investigate. Thus, f of k plus f of k plus 1 is going to be equal to ak plus 1 plus ck plus 1 plus ak plus 2 plus ck plus 2. Oh, but that equals, let me just find out where I am. AK plus 2, let's actually add them together. CK plus 1, FK plus 1 is AK plus 2. We can rewrite the AK plus 2 once again using this formula up here. CK plus 1. And the CK plus 2, same thing really. We can use BK plus 1 for that. And sure enough, can you see, lo and behold, we've got exactly f of k plus 2 here as required. Hope that question made sense. I think it's really quite a nice kind of question from this normally very, very tough paper. Okay, so sorry, about 3 hours has elapsed since I did the last question, so I'm just going to get back into the swing of it. So, question 3. This one I quite liked, although it's really important that you understand, once again, what conditions it's laying down here and here with M and A. It's saying M is bigger than 0 throughout this whole question, and A is less than or equal to -1 throughout this whole question. Now, that's not going to affect your x cubed minus x, which naturally goes through -1, 0, and 1. It's going to affect this line here, this straight line. Now, bear in mind as well, they're making sure that this straight line always touches the cubic. Now, that means it's got a, that is tangent at B. Now, it's well worth thinking about exactly what that means. Like, I'd like to show you on GeoGebra what that means. So if I can just change what the screen I'm